You ever click a button on your screen and just wonder? Like, what is really going on inside that box? Not the high-level stuff, but the actual nuts and bolts journey that turns your one little click into an action. Well, today, we're going to pull back the curtain and follow a single command on its incredible trip right through the heart of a computer. Let's dive in. So here's our plan. First, we'll look at the master blueprint for pretty much all modern computers. Then we'll meet the key hardware players. After that, we'll watch the fundamental rhythm that makes everything tick. We'll follow one instruction from start to finish. And finally, we'll see how a computer handles the unexpected. To really get how your computer works, you gotta meet the guy who drew up the plans. His name was John von Neumann, and his design from way back in the 1940s was so genius it's still the foundation for almost every computer we use today. Now, his big idea, it sounds so simple, but honestly, it changed everything. See, before von Neumann, a machine was built to do one specific thing, kind of like a calculator. His game-changing idea was to store the instructions, the actual program, in the same memory as the data it was working on. This meant you could change what the computer did just by changing the program, not by physically rewiring the machine. It made computers flexible, programmable, and incredibly powerful. So this whole blueprint really just comes down to three basic rules. First, the program and its data are roommates. They live together in the same memory. Second, every single spot in that memory has a unique address, like a house on a street, so the computer can find anything it needs, instantly. And third, the computer follows the instructions one by one, in order, just like following a recipe. This simple, elegant logic is what makes the whole thing work. So let's see how this plan gets built with some real hardware. Okay, so if the von Neumann architecture is the blueprint, who is actually doing the work? The best way to think about it is like a kitchen. You've got the CPU, that's your master chef. You have memory, which is both the pantry full of ingredients and the recipe book. And then you have input/output, or I/O, and that's how the chef gets new orders from the waiter and sends the finished dishes out to the dining room. And here's what that kitchen looks like on a more technical diagram. Over on the left, you've got the CPU, the brains of the whole operation. On the right is main memory, where all the recipes and ingredients are stored. And down at the bottom, the I/O module, which is handling your keyboard, your mouse, your monitor, everything. And see that big line connecting them all? That's the system bus. It's the hallway they all use to talk to each other. Now, let's zoom right into the chef's brain, the CPU. To keep track of everything, it has its own tiny, super fast scratch pad made of things called registers. Think of the program counter, or PC, as a bookmark, always pointing to the next step in the recipe. The instruction register, or IR, holds the step the chef is working on right this second. And the MAR and MBR, they're kind of like the chef's hands, used to point to an ingredient in the pantry and then carry it back. These four are absolutely crucial for the journey we're about to see. Okay, we've got the plan, we've got the players. Now we can get to the main event, the fundamental action, the constant, steady heartbeat of the processor. It's a simple two-step dance that it repeats billions of times every single second. And this is it, seriously. The entire job of a processor, right here in this loop. It starts, it fetches an instruction from memory, it executes that instruction, and then it does it all over again. Fetch, execute, fetch, execute. This relentless, simple cycle is what powers absolutely everything you do on your computer. But of course, it's a little more detailed than that, right? If you zoom in, that simple two-step is more like a carefully choreographed routine. Each main part, the fetch and the execute, is actually made up of several smaller, really precise movements that have to happen in perfect order. Things like before you can fetch an instruction, you got to figure out where it is. After you grab it, you have to decode it to understand what it's even asking you to do. Then you might need to find the address of the data you need. Go get that data. Do the actual math, and then finally store the results somewhere. It sounds like a lot, but a modern processor does this entire sequence in a fraction of a nanosecond. It's just unbelievably fast. All right, that's enough theory. Let's make this real. We are now going to follow one very simple program. It's just 3 instructions long on its complete journey through the processor. We're going to see that fetch-execute cycle live in action. Okay, here we go. Our journey starts right here. The program counter, that's our bookmark, is pointing to memory address 300. So the CPU goes to that spot and fetches the instruction it finds there, which is the number 1940. It then puts that instruction into the instruction register so it can figure out what to do next. And check this out. This next part happens almost instantly.
To be super efficient, the CPU immediately updates the program counter to 301. It's already getting the next instruction lined up before it's even finished with the current one. Talk about a good multitasker, right?
Okay, now for the execute part of the dance. The CPU decodes that 1940 instruction. The 1 is basically the command, load from memory, and 940 is the where. So it zips over to memory location 940, grabs the value it finds there, which is 003, and loads it into a special workspace called the accumulator. This is it. This is the moment data moves out of storage and into the CPU's hands. Boom, first instruction's done. Now we loop back for the next one. The PC is at 301, so the CPU fetches instruction 5941. It decodes the 5 to mean add from memory. So it goes to address 941, fetches the value 0002, and adds it to the 0003 that's already waiting in the accumulator. 3 plus 2 gives us 5. The result, 0005, now replaces what was in the accumulator. All right, we're on the home stretch. One last instruction to go. The program counter is now at 302, which points the CPU to fetch our final instruction, 2941. The CPU looks at the 2 and knows that's the command to store the value from the accumulator back into memory at address 941. And this is the final move. The CPU takes the result 0005 from its accumulator workspace and writes it into memory at location 941, overwriting the old value. And that's it. The program is done. So think about that. That entire sequence, fetching, decoding, and executing 3 separate times, is what it takes for a computer to do one simple addition like 3 plus 2. So that fetch-execute cycle is awesome for just chugging through a to-do list one item at a time. But what happens when you move your mouse or a file finishes downloading? Those are unexpected events that need the processor's attention right now. In the computer world, these are called interrupts. Well, to handle this, the processor adds one tiny little step to its routine. After it executes an instruction, but right before it fetches the next one, it takes a quick peek to see if anyone's trying to get its attention. If there's an interrupt waiting, it'll pause the program it's working on, go handle the interrupt, and then come right back to where it left off without missing a beat. This is the real secret to modern multitasking. Okay, but what if 2 interrupts happen at once? There are basically 2 ways to handle it. The simple way is to just hit Do Not Disturb and ignore all new interrupts until you're done with the first one. It works, but a non-urgent task could end up blocking something critical. The smarter way is to give interrupts priorities. This way, a super important alert, like a power failure warning, can actually interrupt a less important task, like a print job finishing. It's more complicated to manage, but it makes sure the computer is always working on the most important thing first. And there you have it, the journey of a single instruction. It's a simple, elegant dance of fetching and executing, repeated with a speed that's almost impossible to comprehend. And when you realize that billions of these microscopic dances are happening every single second, they all combine to create the entire complex, powerful, and seamless experience of modern computing. It's kind of mind-blowing, isn't it?